Hi scholars, today we're going to talk about exponent laws and sort of make a little sense about where these laws come from. Now we call them laws, but they're really basically, another way of thinking about them are sort of formulas, or we could even call them patterns, right? And these are basically some sort of general patterns, let's call them, that we can use to manipulate expressions that have exponents in them. So for example, expressions like x to the fourth power, that's an expression that has an exponent in it, right? Now we are going to today talk about where these laws come from, and they should be a little familiar to you. I'm sure you've seen them in school before. So if you raise a power to a power, you multiply the exponents. If you multiply the exponent, like the two expressions that have the same base but different exponent powers, you add those exponent powers. When you divide, you subtract. Anything to the 0 power is equal to 1. And then this one, where if you have a negative exponent, it's the same thing as 1 over the positive exponent. So I know this is all a little confusing right now. We're going to go through these one by one with real examples. But just know that all of these laws, it's not that the math gods dropped them down, right, and said, okay, these are the rules you have to follow. They actually make sense. Okay, so let's make sense of them. Okay, so for example, if I have x to the fifth power, all of that thing, that quantity, squared, we want to say, well, how else could I rewrite that? Okay, and let's do it just by sort of writing it all out. So x to the fifth power, if I want to take a look at that, that's just x times x times x times x times x, right? That's what it means to take something to the fifth power. Now, to square something means you take that thing and multiply it by itself, right? 5 squared is 25, because 5 times 5 is 25. So let's take that thing, which is this whole thing, and multiply it by itself. So we're going to multiply it by x times x times x times x times x. And we want to say, okay, we did all that work. How many x's do we have, right? How many x's are we multiplying by? Well, there's 5 here, and there's 5 here. So altogether, there is 10, okay? And then we want to think, what could I do with the numbers 5 and 2 in order to get to the number 10? And the answer is you multiply them, okay? That is law number 1. What do I do when I raise a power to a power? You multiply them. You multiply the exponents. Okay, let's keep going. Number 2, an example of law number 2, x to the fifth times x squared. Well, again, let's write it all out. X to the fifth is x times x times x times x times x. X squared is x times x. And we're multiplying, right? I put these two parentheses just to show that like this is its own separate thing, right? But clearly there's a multiplication sign. There's another dot right there in between these two expressions. And so if I count up how many are there, well, there's 5 here and there's 2 here. So in fact, we end up with x to the 7th power. And then again, we ask ourselves, what can I do with a 5 and a 2 to get to 7? And the answer is we add them, right? And that's where this law comes from. Let's take a look at one more. X to the fifth divided by now x squared. Okay, we can deal with that. So again, we're going to rewrite x to the fifth as all of the 5 x's all multiplied by each other, and we're now dividing by x times x. Okay, now when we divide two numbers that have the same sort of factors in them, we can cancel them out, right? In the same way that we say that 6 divided by 2 is 3, right? The reason why that is because 6 is really 2 times 3, right? Divided by 2. And since I have a 2 and a 2, right? There's a 2 and a 2. I can cancel them because they're the same number, okay? So we're going to do the same thing here. We're going to cancel out all the same the factors. So there's an x on the top and the bottom, so they're both gone. There's an x on the top and the bottom, so they're both gone. And what do I have left? Well, it looks like I have 3 x's left, so let's just write that. So what I have left is x to the 3rd power. And once again, we're going to look and say, what can I do with the numbers 5 and 2 to give me the number 3? And there we are, right? We subtract them. That's where that subtraction comes from when you divide exponents that have the same base, okay? That's important. We'll see that that's important later on. And let's keep going. Now, what if I have x squared divided by x squared? Well, let's think about that for a second. If I have the same number divided by that same number, this is really the same thing as asking, what is 5 divided by 5? Or 3 divided by 3, right? Or my foot divided by my foot, right? And the answer is, it's 1. This has to be equal to 1 because they're the same thing. So I know, before I do any math, I know that this answer is equal to 1. Okay. Now, if I wanted to use that exponent pattern, where I said if I'm dividing, I subtract the bases, okay? I would rewrite this as x to the 2 minus 2 power, right? I subtract the bases when I divide. And that's just equal to x to the 0 power. So by thinking about this expression in one way, we get that it's got to be equal to 1. By thinking about it in a different way, we have that it has to be equal to x to the 0 power. If both of these things are true, it means we can conclude that x to the 0 power is equal to 1. Okay, this is one way of reasoning about this. Now, this is a definition. Mathematicians decided to say x to the 0 power is equal to 1 because it made sense with all the other rules that they had, all the other laws. Okay, so this is an example of sort of like a logical argument, right, of why it must be the case that x to the 0 is equal to 1. So if you want to take another look at that, it's an important idea. And again, we have that right here. There we go. There's x to the 0 is equal to 1 right there. And let's keep going. We got one more. X squared divided by x to the 5th. Okay, this one will be a little different. So, oops. So here I have x times x on the top. And we have 5 x's that were being multiplied to each other on the bottom. And again, we can cancel similar x's. If there's one on the top and one on the bottom, goodbye. One on the top and one on the bottom, goodbye. And when I see what I have left on the top, well, on the top I just have 1, right? Because there's always a factor of 1 everywhere, right? 1 times anything is itself. And on the bottom I have 3 x's left over, so that's x cubed. So one way of reasoning about this is that it equals 1 over x cubed. Again, we're going to do another way of reasoning about it. So another way of reasoning about it is, I know that it's the same subtraction pattern. When I divide two exponents, I subtract. So this should equal also, here, I'll do it in purple, this should also equal x to the power of 2 minus 5. Well, what is 2 minus 5? That's -3. So one way of reasoning about it, we have that this thing is equal to 1 over x cubed. The other way of reasoning about it, we have this thing is equal to x to the -3 power, which means that x to the -3 must equal 1 over x to the +3. Okay, and this is a general rule, and there's nothing special about the fact that we got 3, right? That's what sort of makes it a general principle. And if we go back here, that's exactly what this rule number 5 is saying. Okay, so those are our exponent rules. These are sort of our ways that we can work with exponents, and so let's do it. Okay, so let's use all these laws all together. Let's simplify this ugly thing. So the first step is I'm going to look just on the top, just on the numerator of this expression, and I'm going to say it's x to the 10th power. So okay, that's x to the 10th power times, and here I have a power to a power, right? It's this whole quantity to the -2 power, and I know what I can do. I can multiply the exponents when I have raised something a power to a power. Even if they're negative, it's okay. We can still follow that pattern. So 3 times -2 So here, we'll just keep that. So this is 3 and negative 2. That's going to be negative 6, okay? And we can keep going, and now I'm just going to copy down what I had below here, x to the 4th power, okay? Now what's my next step? Well, I know that if I multiply two exponents that have the same base, right, I can add the exponent powers. That's another of these laws that we learned. So this is actually just all going to equal, on the top here is going to be x to the 10 plus negative 6 is equal to 4, right? I'm adding a negative all over x to the 4th. And now I could use my exponent laws, but no, it's the same thing on the top and the bottom. So I know that this is just equal to 1, right? This is all equal to 1. Or I could write it as x to the 4 minus 4, which is x to the 0, which again is one of our laws that says that it's equal to 1. Okay? And now we say, could we use this same idea to simplify this thing? And we certainly could, right? The only difference, the only difference between this and this is that instead of x's, so everywhere you see an x here, instead of an x, they're just 7s, but that's okay, right? It's the same, exact same operations that are happening to these terms, whether it's an x or whether it's a 7. So to simplify this thing, yeah, this thing is also equal to 1, right? It doesn't matter what the value of the base is, okay? And I think that is it.